The universe is home to some of the most mysterious and awe-inspiring phenomena, and among them are black holes, cosmic giants with a gravitational pull so strong that not even light can escape. But while most people are familiar with supermassive black holes, lurking at the centers of galaxies, there exists a rarer and even more astonishing category: ultramassive black holes. These titans dwarf their supermassive counterparts, with masses exceeding 10 billion times that of our Sun. Take Phoenix A, for example, a black hole sitting at the center of the Phoenix cluster, located 5.8 billion light-years away. Its mass is a staggering 100 billion times that of the Sun, making it the most massive black hole ever discovered. Another contender, Ton 618, is around 66 billion times the mass of our Sun. These behemoths are not just large, they push the boundaries of what scientists thought was possible. This raises an intriguing question: is there a limit to how massive a black hole can grow? Could Phoenix A represent not just the largest black hole ever found but also the largest black hole that can ever exist? These questions lead us into a fascinating exploration of the forces that govern these celestial monsters and the delicate balance that determines their ultimate size. If you're captivated by the mysteries of the cosmos, make sure to like this video and subscribe for more deep dives into the wonders of the universe. Let's embark on this journey together. When we talk about the largest structures in the cosmos, ultramassive black holes stand out as the ultimate cosmic titans. These black holes push the boundaries of size and mass, with Phoenix A and Ton 618 serving as prime examples of their sheer scale. But what makes these objects so extraordinary is not just their size, it's what their existence reveals about the universe itself. Phoenix A, located 5.8 billion light-years away in the heart of the Phoenix cluster, weighs an estimated 100 billion times the mass of the Sun. To put that into perspective, this single black hole could easily encompass the combined mass of entire galaxies. Ton 618, another record holder roughly a billion light-years away, has a mass of around 66 billion suns. These black holes challenge not only our understanding of the cosmos but also the limits of astrophysics. How can such immense objects form, and what are the conditions that allow them to reach these unimaginable sizes? Scientists define ultramassive black holes as those exceeding 10 billion solar masses, a step above the supermassive category, which begins at 10 million solar masses. But where do such colossal black holes reside? Research shows that ultramassive black holes tend to inhabit the brightest galaxies in the universe. These galaxies, known as brightest central galaxies, BCGs, sit at the cores of galaxy clusters, regions teeming with stars, gas, and dark matter. The correlation between a galaxy's stellar mass and the size of its central black hole suggests a profound connection between galaxy formation and black hole growth. Even more fascinating is how these black holes interact with their environments. Their immense gravitational pull doesn't just consume material, it shapes the very galaxies they inhabit. Through powerful jets of energy and radiation, ultramassive black holes regulate star formation, heating surrounding gas and preventing it from condensing into new stars. These interactions highlight the dual nature of black holes. They are not just destructive forces but also cosmic architects, sculpting the galaxies around them. The existence of these giants raises a compelling question: are there even larger black holes waiting to be discovered, or have we already encountered the upper limits of their size? As we unravel the mysteries of Phoenix A and Ton 618, the answers may redefine our understanding of how these celestial behemoths come to be. And just as we marvel at their incredible scale, we're left with a tantalizing thought: what lies beyond these giants? Could the universe still hold surprises in the form of even more colossal black holes? Stay with us as we dive deeper into the forces and mechanisms that govern these cosmic monsters. The sheer size of ultramassive black holes like Phoenix A and Ton 618 seems limitless, but their growth is anything but unchecked. In fact, the universe has a natural system of checks and balances that regulates how massive these black holes can become. This mechanism is both elegant and powerful, shaping not only the black holes themselves but also the galaxies they inhabit. At the heart of this regulation is the flow of gas. Black holes grow by consuming gas and other material that falls into their gravitational grip. But as they feed, they release colossal jets of energy, streams of high-energy particles that blast outward at nearly the speed of light. These astrophysical jets don't just radiate energy, they actively reshape their surroundings. When these jets collide with surrounding gas, they heat it up, preventing it from cooling and condensing into new stars. This stifles star formation in the galaxy and, more importantly, cuts off the supply of fresh material that the black hole relies on to grow. It's a self-regulating cycle. The more the black hole feeds, the more it disrupts the very environment that sustains it. This feedback loop is crucial because it creates a natural limit to black hole growth. As the gas in the galaxy's central regions is consumed or pushed away, the black hole's food supply dwindles, eventually stunting its growth. For ultramassive black holes, this limit appears to hover around 100 billion solar masses, an extraordinary number, but one that seems to define the upper boundary of what nature allows. Interestingly, this regulation doesn't just apply to ultramassive black holes. It influences galaxies on every scale, tying the growth of black holes to the formation of stars and the evolution of galaxies. This intricate balance ensures that black holes don't consume their galaxies entirely or grow beyond the universe's capacity to sustain them. The process reveals a fascinating truth: black holes, often seen as forces of destruction, are also forces of equilibrium. They sculpt their galaxies, dictate star formation, and set the stage for cosmic evolution. But if this natural mechanism limits their size, what does it say about the largest black holes we've already discovered? Have Phoenix A and its counterparts already reached their ultimate growth potential, or is there still more room for them to expand? As we explore these questions, the intricate dance between creation and destruction continues to unfold, offering a deeper understanding of how the universe maintains balance in even its most extreme environments. For decades, scientists have marveled at the sheer scale of ultramassive black holes like Phoenix A, wondering whether there's a ceiling to their size. Could there be a limit to how much mass these cosmic behemoths can accumulate? Recent research suggests that there is, and it all comes down to the delicate interplay of forces that govern their growth. Astrophysicists estimate the maximum mass of an ultramassive black hole to be around 100 billion times that of the Sun. This theoretical limit isn't just a random number, it reflects the intricate dynamics of how black holes feed and interact with their surroundings. As we've seen, a black hole's growth depends on the availability of gas and other material. However, the feedback mechanisms that regulate this process, jets of energy, radiation, and outflows, also serve as a natural brake, slowing down and eventually halting their expansion. Phoenix A, sitting at approximately 100 billion solar masses, may represent the pinnacle of black hole growth. It could very well be the largest black hole we'll ever encounter, not because larger ones are impossible, but because the conditions required for their formation and sustenance are exceedingly rare. It's as if the universe itself has set a cosmic threshold, ensuring that even these titans adhere to the rules of balance. But why does this limit exist? It's tied to the broader structure of the universe. Black holes grow most efficiently in the brightest and most massive galaxies, those at the centers of galaxy clusters, like the brightest central galaxies, BCGs. These environments provide the vast reservoirs of gas necessary to fuel black hole growth. Yet, as black holes grow larger, their energy outputs also intensify, disrupting these reservoirs. The more they consume, the more they starve themselves, creating a natural endpoint. This idea challenges our perception of black holes as infinitely voracious entities. Instead, they're part of a system of cosmic checks and balances that shapes galaxies and clusters alike. Phoenix A may be an outlier, but it's also a testament to the universe's remarkable ability to self-regulate, even in the face of its most extreme phenomena. And yet, even as we contemplate the upper limits of black hole growth, questions remain. What happens if a black hole reaches this theoretical maximum? Does it simply stop growing, or do we discover new mechanisms that allow it to transcend the apparent limits? Could there be regions of the universe, perhaps in distant epochs or untouched corners, where the conditions for even larger black holes exist? These mysteries are at the forefront of astrophysical research, pushing us to rethink what we know about the universe's most colossal entities. As we grapple with these questions, the story of ultramassive black holes becomes not just a tale of limits, but also one of endless possibilities, hinting that the cosmos may still hold surprises far beyond our current understanding. While the limits of ultramassive black holes like Phoenix A captivate our imagination, scientists are turning their attention to another, less understood class of black holes: intermediate mass black holes. These cosmic enigmas, with masses ranging from 1,000 to 10,000 times that of the Sun, represent the missing link between stellar mass black holes, formed from collapsing stars, and their supermassive counterparts at the centers of galaxies. Intermediate mass black holes are elusive, hiding in the shadows of our observations. Unlike supermassive black holes, which dominate galaxy cores, or stellar mass black holes, which are often detected in binary systems, these mid-sized black holes are harder to pinpoint. They may reside in dense star clusters, dwarf galaxies, or even as wanderers in intergalactic space, far from the regions we traditionally associate with black hole activity. Finding them is no easy task. Their faint gravitational influence and lack of bright accretion disks make them challenging to detect. However, advances in technology, such as gravitational wave observatories and high-resolution telescopes, are beginning to reveal their presence. Observing their interactions with stars or detecting subtle shifts in the motion of celestial objects offers glimpses of these hidden giants. Why do intermediate mass black holes matter? They hold the key to understanding black hole formation and growth across the cosmos. Did ultramassive black holes like Phoenix A grow directly from primordial seeds, or did they form through mergers of intermediate mass black holes? Answering this question could unravel the evolutionary history of black holes and provide insights into the earliest stages of the universe. As scientists continue their hunt for these elusive objects, the study of intermediate mass black holes promises to bridge the gap between the extremes of black hole science. From the smallest stellar remnants to the titanic ultramassive giants, this hidden population may be the missing puzzle piece in understanding the life cycle of these extraordinary cosmic phenomena. The search reminds us that, even in the vastness of space, there are still countless mysteries waiting to be uncovered.